And thank you for invitation of this good, nice conference. And today I'd like to explain how to construct the lattice of wide subcategories from the lattice of torsion classes by using a purely lattice theoretical way. And this is the setting of today's talk. Lambda is a finite-dimensional algebra, and we consider the category of finitely generated right lambda modules. And maybe most of you know torsion classes and wide subcategories. Torsion class is a subcategory of mod lambda, which is closed under extensions and quotients. And tos lambda denotes the poset of torsion classes, where the poset structure is usually inclusion of subcategories. And wide subcategory is a subcategory which is closed under extensions, kernels, and co-kernels, so abelian subcategories. And similarly, we can consider wide lambda, the poset of wide subcategories. And these two posets are actually complete lattices because torsion classes and wide subcategories are closed under taking intersections. So meet operation is just an intersection, and we have an extra join operation for these posets. And in today's talk, for simplicity, I assume that post lambda is finite. Namely, lambda is tau-tilting finite algebra. And the situation is that we are given post lambda just as an abstract lattice, and we don't know any information about mod lambda, original algebra mod lambda. And from this information, I will construct the poset wide lambda. And this is my working example in this talk. Consider the A2 quiver, and the Hasse quiver of tos lambda is given like this, so pentagon lattice. And the situation is that we are only given this lattice. And this is the starting point. And from this lattice, the first thing I will do is to give a labeling of each Hasse arrow. So consider the Hasse arrow from A to B. So this is A covers B, so minimal inclusion of torsion classes. Then we can label its arrow by particular elements of tos lambda by this formula. So this is the label gamma A from A to B. This arrow is the minimum element of this set. This set is X such that the join of B and X is equal to A. So B is smaller than and consider such X and take the minimum one. Actually, there exists a unique minimum element, and so it's well defined, and this is called join irreducible labeling because this element satisfies some nice property, but I don't explain it today. And so let's look at the example. Consider this arrow from 1 to Z. Then the join of, for example, Z and X is equal to 1, but also the join of Z and Y is also equal to 1. And Y is smaller, and the label is Y. So we take smaller one. And in this, this labeling is only depends on the lattice structure. By using this map labeling, Bernard Todorov to introduce the kappa, extended kappa map as follows. Actually, this is not the same definition, but it's equivalent. Definition is that for each element X, there exists a unique element kappa over of X satisfying this equality, and maybe this is easier to understand. So the set of labels of Hasse arrows starting at X, so lower labels, is equal to the set of labels of Hasse arrows ending at this element. And this claims that for any element, there exists such element, and there exists actually unique element. And in this way, we can define map, which is called the extended kappa map. So consider this example. So this is the formula. For example, consider element X, and the lower label of X is only X, and we have to find an element such that upper label is only X, and such element is Y. And similarly, y goes to z and z goes to x. And 1 goes to 0 because the lower level of 1 is y and z, and the upper level of 0 is y and z. So we have this extended kappa map, and by using this kappa map, we can define a new partial order poset structure on tos lambda as follows, which I call the kappa order. For two elements x and y, we define x this relation by following. So x is less than or equal to y in the original poset structure, and by applying the extended kappa map, the relation reverses. So kappa of x is greater than or equal to kappa of y. And in this case, we write this. So this is clearly a new poset structure, which is stronger than the original poset structure. And the main theorem of today's talk is this, and actually this is in my paper on today's archive. And so the main result is that wide lambda is isomorphic to tos lambda together with this kappa order. Actually, there is a natural map from wide lambda to tos lambda by taking the smallest torsion class containing each wide subcategories, and this map induces this poset isomorphism. And the interesting thing is that this works with a little modification for any abelian length category. So we don't have to assume that tos lambda is finite, but we have to restrict some conditions. And so let's look at the example. Working example, this is tos lambda. This red line is kappa, the extended kappa map, and the kappa order is this. So, and by main theorem, this is isomorphic to the lattice wide lambda. And for example, consider x and y in this, and in the original poset structure, y is smaller than x, but consider the kappa order. So applying kappa map, y goes to z and x goes to y. And y and z are not comparable. So x and y are not comparable in this kappa order. And in this way, we get this poset. And finally, I would like to talk some properties, lattice theoretical properties of the lattice of wide subcategories and some conjectures. And I think the lattice wide lambda is a very interesting object. And so for example, we can prove that the lattice wide lambda is ranked lattice or graded lattice with rank function given by the number of simple objects of wide subcategories. For example, so this is the Hasse diagram for some algebra with maybe rank 5. This is the and this looks very beautiful. And the Aoki, Higashitani, Iyama, Kase, Mizuno's paper in preparation shows that the rank vector is symmetric and unimodal. So rank vector is the number of elements in each rank. So in this case, this is the rank vector. And this is symmetric, and unimodal means that it goes bigger and then smaller. So very symmetric. Wide lambda has very symmetric form like this. And this is some conjecture of this lattice. And I don't explain detail about these conditions, but I conjecture that wide lambda has Spelner property, and rank vector has a very nice property, and it has the symmetric Boolean decomposition looks like this. So it must be it seems that wide lambda has a decomposition into Boolean lattice with the same center as in this picture. And finally, I'd like to introduce my program. Actually, my talk is combinatorial, so we can do computer computation by, and actually I developed such program in Sage Math, and this is a link, maybe you can click, and this is a YouTube video link. And so that's all. Thank you for listening.